Welcome. We are studying AC bridges, and so far we have learned to design bridges, product or ratio bridges, in product or ratio form. Okay. Now, there are bridges also which are not in product or ratio form, neither in product form nor in ratio form. They have special reasons why they are in that form. So, we will see today a bridge which is called Wien bridge. Once again, you need not remember or memorize these names at all, which bridge is which type. This is only for your information. Okay. So, this particular bridge is just a capacitor bridge which has two resistances and two capacitor branch. Okay. And had it been a nice ratio bridge, we should have this element, this branch, as a parallel combination of capacitor and resistor. Okay. Then the balance equation becomes easy, but we will have the R and C in series. This is a peculiar bridge. This is not a nice ratio bridge. You may still call it a ratio bridge because the two adjacent arms are purely real. Okay, so R1, C1, C2, R2, R3, R4. These R3 and R4 are purely real. So, you may still like to call it a ratio bridge, but at least it is not a nice ratio bridge. Balance equation is not going to be very simple. Okay. This bridge, this is a peculiar bridge which is called Wien bridge. So, let us see the balance equation. I urge you, I request you that you try to derive it yourself by pausing the video and match the answer with me later. Okay. So, how do we proceed? We will proceed by the simple rule Z1 by Z2 equal to Z3 by Z4, like that. Okay. So, let us write this as Z1 is R1 plus 1 over j omega C1, this branch. Okay. And okay, let me multiply this with R4, and here let us write this branch Z2. Now, Z2 will be parallel combination of this two. So, that means R2 by j omega C2 divided by R2 plus 1 over j omega C2. This is the parallel combination of R2 and C2 whole multiplied by R3. Okay. Now, we have to simplify this equation. Okay. So, the right side, let us take a product of these two terms. Okay. Let us do it this way: R1 plus 1 over j omega C1 multiplied by R2 plus 1 over j omega C2. Then this I can write R2 by j omega C2 R3, this part, and R4, I missed R4, let me keep R4 here. Okay. So, you see this balance equation is not going to be easy, although we can derive it from the first principle that product of this two should be product of this two. Okay. But this is not going to be easy. That is the problem with bridges which are not nice product or ratio bridges, but we can do it. And now, if I make a small mistake, the answer may come out wrong. So, please check the calculation also yourselves. Okay. So, let me take the product R1 R2. This is a real number, then minus this 2, or let me do it this way, plus 1 over j square which is minus 1, then omega square C1 C2. Okay. So, this is the real part, and then I will have the imaginary part as R2 by j omega C1, R2 by j omega C1 plus R1 by j omega C2 whole multiplied by R4, and the right hand side is R2 R3 by j omega C2. Right hand side is purely imaginary, left hand side is a combination of real and imaginary. So, which means I will have two conditions. Condition 1, so if I equate the imaginary part first. Okay. So, the imaginary part here is R2 by C1 plus R1 by C2, okay, whole multiplied by R4. This j omega and this j omega will cancel. This will be equal to R2 R3 by C2. Okay. And then from the real part in the left hand side is R1 R2 minus 1 over omega square C1 C2 whole multiplied by R4. Right hand side, the real part is 0. Okay. So, R4 cannot be 0, resistance cannot be 0. So, this has to be the condition, therefore. So, from this we can write also that omega square, okay. So, that this 2 should be equal, if this is 0, then omega square will be equal to R1, sorry, not R1, 1 over R1, 1 over R1 R2 C1 C2, or omega will be, so you can write this as okay. So, these are the two balance conditions. This is 1, this is 2. Okay. So, please try to derive this yourself. If you just watch it, do not practice, then it is likely you are going to make mistakes in exams and in other places. Okay. Please practice, please practice. Okay. So, now, so these are the two balance equations, which means if now we can adjust these impedances and get this balance bridge, get this bridge balanced, and therefore, if one of these sides is unknown, say these are unknowns, then by adjusting this we can get the bridge balance and find the value of these unknowns using this equation. That is possible, but the balance equation will depend on the frequency. Okay. So, if you see here, the balance equation depends on the frequency. So, we need to know what is the frequency of the supply voltage. Then we can only measure the unknown impedance branch. That is one possible way of using this bridge. But this bridge is used for a completely different purpose. This is not used to measure an unknown capacitor or any unknown impedance. This bridge is used to measure an unknown frequency. This bridge is used to measure unknown frequency. Instead of unknown capacitor. Okay. Because you see, the balance equation depends on this frequency omega. So, therefore, you can also adjust the frequency of the supply voltage. If this is omega, if this frequency is omega, angular frequency is omega, which means omega is actually 2 pi f. F is the frequency in hertz, this is in radian per second. You can also vary omega. Okay. So, to get this bridge balance, or if omega is an unknown frequency, then omega is constant, then you can vary these parameters R, C, etc. to get this bridge balanced, and from that you can measure the value of omega. So, we can vary these impedances R1, R1, C1, etc. all these things, R1, C1, R2, C2, R3, R4 for a given, that means fixed unknown frequency. And once we get the balance, from that, using this equation we can measure the frequency omega, and then from the balance condition we can measure frequency omega as this, or if you want to measure, so f, this is equal to 2 pi f. So, you can divide this by 2 pi to get f. So, this is called Wien bridge. So, the lessons are, there are bridges which are not simple product and ratio bridges. There are special purpose bridges like this Wien bridge, which is used for frequency measurement. Another lesson is that if the bridge is not a nice product or ratio bridge, the balance equation becomes difficult to find, but we can still find it using the first principle Z1 by Z2 equal to Z3 by Z4, so on, like that. Okay. Now, there are also other bridges which are not again simple product and ratio bridge. Let us see one such bridge which is very peculiar. So, this looks like this. This is an unknown inductor X, X for unknown. This is R, R1, this is our what do you want to call it, one this we will call R4 according to the notation that we are using so far, 1, 2, 3, 4, but this part is peculiar. Now, okay, let me just name them arbitrarily, R3, C3, R5. The detector, the null detector is placed here and the supply is applied here. This is the voltage source. This is a peculiar bridge. This is called Anderson bridge. Okay. You are not at all expected to remember this bridge. We are not expecting that, we are not going to ask you that draw Anderson bridge, how does it look like? No, 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 not at all. Do not memorize it. What we may ask you that given this bridge, can you find the balance equation using the knowledge of circuit theory? Okay. So, you are expected to find the balance equation of any complicated bridge. You are not expected to remember this structure of these peculiar bridges, not at all. Okay. So, balance equation. How can we find the balance equation? This does not look like a 4-arm bridge, 4-side bridge which we are familiar with. Okay. All the bridges that we have studied are all 4-arm bridges where the detector is placed like this and the supply is here. This is the standard bridge. But this does not look like that. Okay. So, how do we find the balance equation? Using the knowledge of circuit theory, we can convert this bridge into this form. How? There are many ways. One possible way is this. So, look at these 3 arms R3, C3, R5. So, they form a delta. You can convert this into a star. If you do this conversion, this delta to star conversion, then this bridge will look like so using delta to star conversion. If we do this, then R1 will be as it is, this will remain as it is, R4 will remain as it is, this part will change its shape. So, currently it is like this, but now this will become some impedance here, some impedance here and some impedance here. So, this is a star. Okay. Supply is here, and you can find the value of these impedances. Call this as ZA, ZB, ZC, and the detector is here. Okay. Now, the value of Z, A, B and C can be found from star delta conversion using, say, Z A. This will be equal to the product of these two, this and this, which is same as R3 R5 divided by the sum of this 3, which is R3 plus R5 plus 1 over j omega C3. This is Z A. Similarly, Z B is this. This will be R3 C3, not C3, 1 by j omega C3. The impedance of this multiplied by this, whole divided by the sum of all three, R3 R5 plus 1 by j omega C3. ZC equal to something similar. This is your homework. Now, once you find this Z A, Z B, Z C, then this bridge looks like a 4-arm bridge. Which are these 4 arms? This is one arm, okay, from here to here. Then say this is another arm, then say this is the third arm, of course, and then running out of color, okay, this is the fourth arm. The detector is between this ZB you can think as integral part of this detector or internal resistance of detector. So, ZB, this two you think together with the detector. So, therefore, the balance equation now can be written as R1 plus ZA. This is this red branch divided by ZC. This is this violet branch. This is equal to this Lx plus Rx, means j omega Lx plus Rx divided by R4, and ZB can be thought of the internal resistance, not resistance, impedance of the detector, null detector. Okay. So, now ZB has no role, ZA is here, ZC is here. You can find these values and put it in this equation, and from that you equate the real to real, imaginary to imaginary, you will get 2 equations. Okay. So, finish the derivation, this is your homework. Finish the derivation. Okay. So, I can do it in many ways. Now, I will show you another way of finding this derivation, this balance equation, which will be easier, I feel. What we will do, okay, so we are going to see a easier method where instead of converting this delta into a star, observe that these 3 arms, they form a star. Okay. So, these 3 arms, 1, 2 and 3, they form a star. I will convert this star into a delta like this, 1 arm, second arm and this will be the third arm. Okay. So, we will apply a star to delta conversion. Okay. So, this star is not easily recognized. This delta, I mean often we recognize this delta very quickly, but this star is not easy to recognize, but once you recognize the derivation becomes easier. How? Now, okay, so let us draw the equivalent circuit. In the equivalent circuit, this branch will remain as it is. This will remain as it is. Then the detector, and even this capacitor will remain as it is. So, this capacitor is not going to change. So, C3 as it is, okay. But this 3 R1, R3 and R5, they will change. Okay. Let me call this terminals as A, B and C. Point A, point B and point C. This is point A, this is point B, this is point C. Now, we will have a branch between A and B, this branch. So, this will be call it ZAB. We will have a branch between B and C, call it ZBC, and between A and C, call it ZAC. Okay. Now, the supply is here between A and C. So, the supply is here. Okay. Now, can we find the values of ZA, ZB, ZC? Yes, that is simply delta to star conversion. And once we find this ZAB, ZBC, ZCA, then you observe now that ZAC has no role. This is simply in parallel with this voltage source. So, it is drawing some unnecessary current, some extra current which is not going through the bridge. So, ZAC can be thought of as a integral part of this source system, supply system. So, ZAC has no role in the balance equation. Okay. And this part is now a 4-arm bridge. What are the 4 arms? The 4 arms are, this is one arm ZAB, these two together. Okay. So, this is one arm, this is one arm, then these two together is another arm, then this is obviously the third arm, and this is the fourth arm, fourth side. one side, second side, third side and fourth side, and between these two opposite terminals we have the detector, and between these two opposite terminals we have the supply. Therefore, the balance equation we can write ZAB by this thing okay. ZAB by this is same as j omega Lx plus Rx, this branch, divided by R4. This way we can find the balance equation. Now observe what are these values of ZAB, ZBC, ZCA. These are all going to be resistances. Why? Because these three original star connected elements, they were resistances. So their equivalent delta will also be resistance, of course. So you can call this RAC, RBC and RAB instead of Z. We know they are going to be resistances. And what is the value? The value is say this ZAB, or you can call it RAB, will be same as sum of these products R1, R3, 1, 3, 3, 5, 5, 1, 1, 3, 3, 5 and 5, 1. This is the formula for star to delta conversion divided by the opposite arm. Okay. So, for AB the opposite arm is this R5, okay, which is not connected to A or B, R5. Similarly, this branch which is ZBC, or you can write this as RBC because this is going to be resistance. So, this will be this product 1 3 3 5 5 1 whole divided by the opposite arm to this, and opposite one is in this case is R1. This R1 is not connected to B or C. Okay. So, this is the opposite one. So, this is the formula, and ZCAC you can also find this way, but this is not useful because it is not going to be in the balance equation at all. Okay. ZAC is not required. So, okay. Now, we can put these values in this in this equation. So, we can put these values of ZBC from here and ZAB from here in this equation to get the balance equation. But instead of doing it blindly, let us do it cleverly, because observe that this is now actually a product bridge. Observe, this is a product bridge. These two opposite arms, this red and the orange one, they are pure resistances. Okay. And this is inductance in series, this is capacitance in capacitor in parallel. So, this is a simple product bridge. Actually, this is Maxwell's bridge, which we have seen before. Okay. So, let me go back and show you this bridge. Let me go back. So, this was our Maxwell's bridge. This is the Maxwell's bridge, right, or this one. same, this is the Maxwell's bridge. L are series, C are parallel, R R. Same thing here. LR, RC, RR. So we can actually do it much quickly by recognizing this fact. So we can now write the balance equation. Product of these two, ZAB or RAB, RAB times R4 should be same as the product of this branch and this branch, which is J omega L x plus R x multiplied by this branch. Okay. But instead of putting the impedance here, I can put the admittance here. So I put the admittance of this branch, which will be 1 over Z BC or RBC plus 1 over not 1 J omega C3. Okay. So from this we can write real part Rx will be same as the real part here RAB R4 by RBC, and the imaginary part Lx, G omega will cancel, will be same as C3 times this C3 R4 multiplied by RAB. Okay. So now you can put the values. So RAB by RBC, RAB is here and RBC is here. So RAB by RBC, this part will be same as 1 over R5 divided by 1 over R1. So R1 by R5 this part will cancel, multiplied by R4, this R4, this is Rx, and Lx, you just put the value of RAB, which is this R1 R3 plus R3 R5 plus R5 R1 whole divided by this R1. So that's simple. Okay. So what have we learnt? So we have learnt here to find the balance equation of even complicated bridges using the idea of the first principle Z1 by Z2 equal to Z3 by Z4. Okay. And we have to do it cleverly. We have to apply the knowledge of circuit theory cleverly, so that the calculation becomes easy. That is what we learn in electrical engineering, how to solve, reduce circuits cleverly into simple ones. Okay. You are not supposed to remember the names or the structure of these complicated bridges. You are expected to be able to find the balance equation of any bridge, however complicated it may look like. This is one thing. Second thing, you are expected to able to design simple bridges, product bridges and ratio bridges to achieve particular purpose, like to measure an unknown inductor or an unknown capacitor under some constraints, like you cannot use a standard inductor, you have to maintain the safety of the operator. These are the things you are supposed to learn. Last small thing I will add in this class. You may ask, why do we use such complicated bridges, while when we can measure unknown inductance, capacitance using simple product and ratio bridges? Why do we have Anderson bridge? If you recall, we said bridges are designed using or keeping two factors in mind. One, how simple the bridge is, how simple the balance equation is, and factor 2. Okay. So, let me show you, let me go back. I wrote this once to the way to choose how to design a bridge. Depends on these two factors, how simple the bridge is, and the factor 2, how easily the bridge will converge. We have discussed in detail about the ease or simplicity of the bridge, but we haven't talked about the convergence of a bridge. Let me briefly tell you what I mean by this. What I mean is that in an AC bridge, we measure an unknown impedance, and an unknown impedance has normally two unknowns, two variables. Okay. So, in AC, with AC bridges, we measure unknown impedance which has two parts, like the real part and imaginary part, or you can think the like the resistance and inductance, capacitance and resistance. Okay. So, it has two parts. So, two unknowns, actually two unknowns. So, therefore, we need at least two controls or two variables. Or adjustables to get the balance. Okay, at least two. Okay. For example, let us talk about Maxwell's bridge. Here we have two unknowns, L and R, and we at least need these two to be variable, R3 and C3, at least two. Okay. We can keep these two fixed. It is possible in theory by keeping this fixed and varying only this to get the balance. Although sometimes it may be convenient to adjust this also, but at least two variables are to be adjusted. Okay. Minimum two variables are to be adjusted. And how do we do it? We do it iteratively in lab. So, in the lab we do it. So, in lab we adjust two variables iteratively, like first adjust a resistance, get the minimum deflection as close to null condition as possible, okay, increase or decrease a resistance, and then when you go to the minimum deflection point, then keep that resistance fixed, then change say another thing like a capacitor, okay. Then you go as close to possible to the null condition and then keep the capacitor fixed at that point, and then adjust the resistance again, reduce the deflection as much as possible, and then again change the capacitor. So, change the resistance up or down, reduce the deflection to the minimum value, then keep it fixed, then change the capacitor to some value, make the deflection as small as possible, keep it fixed, then change the resistance again, go to some value, change the capacitance again, go to some value. This way we have to find the balance equation. It is difficult, it is boring and iterative. In lab it is really very boring. You have to change two things at least iteratively. In case of DC bridges, we have to choose only, we have to adjust only one resistance, DC bridge, Wheatstone bridge. We can keep two resistances fixed and vary only one to get the balance. That is easy. But here we have to choose, we have to vary at least two elements iteratively, one then other, one then other, and this could be very boring and time consuming. And with a proper design of the bridge, like what to put in which arm, resistance, capacitance, inductance, with a proper choice, it is possible to have a bridge which is easily balanceable, which will go to the balance condition very easily by only few trials, 2-3 trials. We say the bridge will converge to the balance condition very easily. So, in early days, I think 1930s or 40s, when people thought about these bridges, one of the considerations they had in mind is which bridge is easy to balance, where we can find the null condition very quickly. Okay. So, people thought about that also. So, under different situations, people have therefore designed complicated bridges which are not simple product or ratio bridges. Okay. There are complicated bridges like Anderson bridges where people have thought about this convergence also, how quickly we can go to the null. That is why we have these complicated bridges also. That is actually a very interesting topic, but we cannot cover everything in this course. If possible, in some additional video, we will talk about that, something about that, not very detailed if possible. Okay. So, this is all about AC bridges which you are supposed to know for this course. If time permits and if you are interested, we can have additional videos covering additional topics, not for the exam, but for our knowledge. If you want, we will definitely do it. Thank you.